I'd like to briefly talk today about scale, and not necessarily in terms of the total number of things digitized. Instead, I'd like to focus more on the actual size of the individual things being digitized, and how the further ends of either side of the spectrum can affect our imaging tools and methods. So let's start with small things. This is a roughly 19 millimeter long item from the Connecticut State Museum of Natural History's Caldwell collection of Neolithic Mali points. Automated image acquisition and blended post-processing techniques can be integrated into powerful imaging pipelines. Here's a shot of our lab's programmable macro rail system being used in automated focus bracketing and 360 turntable capture of that same point. On the computational side, source image brackets can be focus stacked in software and then imported into photogrammetry programs for further processing. This can result in sub-millimeter levels of both visual and geometric 3D data. Of course, such multi-process computational pipelines require good and often substantial amounts of raw data to achieve such high fidelity. Another project that we've recently finished was in collaboration with two of the world's preeminent cicada experts. They happen to be Yukon researchers from the Department of Ecology and Evolutionary Biology. This is an opened, pinned specimen box from one of the small batch deliveries that I received during this collaboration. Our goal was to create high-resolution 3D data of representative specimens of all 7 of the North American periodical cicada species, both male and female. So 14 total specimens plus 2 additional ones of atypical variants. Here's a male with spread wing. As you can see, I've mounted the pinned insect on a piece of kneadable art eraser that sits on top of a small Cognisys turntable. It's the same automated focus rail and turntable rig that was used for the previous Stone Points project. With AI assistance, you can then automate object selections across large batches of images in Photoshop. These selections can be inversed and then saved as alpha channel masks within each image, where those same masks can be subsequently imported into photogrammetry software, which allows the application to ignore the background of the image and be more accurate and computationally efficient. We eventually upload rendered models to custom Sketchfab collections for broader access. These are the stone points, and here are the cicadas. We also use Internet Archive to host the more comprehensive data sets of each object. These compressed zip archives contain alternative rendered 3D formats, process reports, and all source images to better increase the transparency of our methods and preserve our work. The datasets also allow anyone to download and reprocess this source information in ways that they see fit with the tools of their own choosing. Here, my Yukon collaborators have embedded Sketchfab models into their own species mashups that also contain streaming audio calls and songs, as well as species distribution maps. Of late, our lab's also been exploring the other end of the spatial scale using drones and aerial photography. This is a DJI Mavic 3 Enterprise with attached RTK module. It carries a 4/3 20 megapixel CMOS sensor, 24 millimeter equivalent lens, and mechanical shutter that allows for sharp photos even while the drone is in uninterrupted automated flight. RTK, or real-time kinematic, allows for much greater flight control versus the GPS-only navigation of consumer drones. RTK units can act as receivers to gather data from satellites and reference base stations to receive differential corrections in order to achieve absolute centimeter level accuracy for positioning and mapping data. This positioning data then gets automatically written into individual images as the drone moves and captures shots. If you couple all of this goodness with automated mission control applications, you can program high-volume, automated image captures across the facades of various structures. Here's a pipeline bridge from DroneLink's website used as an illustration. Think for a moment of an automated XY imaging system in a studio or lab, but replace the movable table or easel with a camera-equipped airborne drone. Many of the movement parameters and imaging concerns are similar between the two types of systems. It's just that these factors are translated a bit differently in untethered airborne space. In the end, here's what you can achieve by combining good image data acquisition with photogrammetry. With automated flight, the resulting camera networks are efficiently and predictably captured across long distances and can be supplemented with manual flight routines around sensitive and tight areas. Positioning data acquired through RTK and embedded in each image are also leveraged during photogrammetric processing to correctly scale and accurately place the object in geographic space. For the Wilbur Cross building, I shot 3,393 images over the course of 4 days while flying roughly 1.5 hours per day. Metashape Pro was able to then successfully align all of these images without a problem. This is one of those 3,000 shots. And here's a sample of the resulting geometry that was partially derived from that shot. This is a depiction of an automated orbit mission that I programmed and executed in DroneLink. The application made easy work of what would have been a particularly laborious and imprecise stick-controlled flight around this cupola. Lastly, the fruits of even larger orbits can be repurposed into thrilling Gaussian splatting-based visualizations.